History of nuclear fusion. Latest advances in nuclear fusion. Comparison of current nuclear fusion startups.
Introduction.
Nuclear fusion represents a potential solution to the world's growing energy needs, providing a nearly inexhaustible and clean energy source. This process, which powers the sun, involves combining light atomic nuclei to form heavier nuclei, releasing vast amounts of energy in the process. The pursuit of practical nuclear fusion has a storied history marked by scientific breakthroughs, technological challenges, and the rise of innovative startups. This report explores the history of nuclear fusion, recent advancements, and a comparison of current nuclear fusion startups.
History of nuclear fusion. Early research and development. Nuclear fusion research began in the 1950s, initially linked to atomic weapon development during the Cold War.
The 1958 Atoms for Peace Conference catalyzed the shift of fusion research into the public domain, leading to collaborative efforts among scientists worldwide.
By the 1970s,
fusion research evolved into a big science initiative requiring substantial funding and international cooperation. The first significant experimental fusion devices were built during this period.
The tokamak, developed by Soviet physicists Andrei Sakharov and Igor Tamm, became a primary focus.
Tokamaks utilize magnetic fields to confine hot plasma, a critical step toward achieving fusion.
Major milestones. Some key milestones in fusion history include:
1. 1952, the first successful hydrogen bomb test demonstrated the power of fusion.
2. 1978, the Joint European Torus jet project was initiated, becoming the largest tokamak in operation.
3. 1991, JET achieved a significant milestone by producing controlled fusion power for the first time. 4. 2006, the International Thermonuclear Experimental Reactor ITER project was formally launched, involving 35 nations, aimed at demonstrating the feasibility of fusion as a large-scale energy source.
Recent advances. In recent years, notable advancements have rekindled interest in fusion technology. In December 2022,
scientists at the Lawrence Livermore National Laboratory achieved fusion ignition, marking the first time a fusion reaction produced more energy than was input to initiate it. This breakthrough is considered one of the most significant scientific achievements of the 21st century.
Latest advances in nuclear fusion. Technological breakthroughs. Recent technological advancements have focused on improving plasma confinement and achieving ignition.
Inertial confinement fusion (ICF), the National Ignition Facility in the U.S. demonstrated record energy output through laser-driven fusion experiments. Magnetic confinement fusion (MCF), the European Joint Torus jet achieved an output of 11 megawatts, setting a new record for sustained fusion power output.
Government and private funding.
Significant funding has been directed toward fusion research, with over $4.7 billion invested in fusion startups. Governments, including those of the US, UK, and Germany, have begun to support private fusion companies alongside traditional research institutions, reflecting a growing belief that fusion could be a viable energy source in the coming decades. Comparison of current nuclear fusion startups. The landscape of nuclear fusion startups is rapidly evolving, with various companies pursuing different technological approaches.
Here's a comparison of some leading startups. 1. Helion Energy. Technology: magnetic target fusion. Timeline: aims for a 50 megawatts fusion reactor by 2028. Funding: raised significant private investment and contracted with Microsoft for future energy supply.
Status: active research and development with a focus on compact fusion reactors.
2. General fusion. Technology: magnetized target fusion, involving liquid metal compression. Timeline: plans to build a demonstration plant by 2025. Funding: backed by various private investors and government grants. Status: actively testing and refining their technology. 3. Gauss fusion.
Technology, focus on advanced materials and magnet design for fusion. Timeline, no definitive public timeline as it is still in early development stages.
Funding, recently established with backing from various European tech firms.
Status, as a new entrant still developing foundational technology.
4. Tokamak energy.
Technology, spherical tokamak using high-temperature superconducting magnets.
Timeline, aims for commercial fusion electricity by 2030. Funding, received government support and private investments. Status, achieved significant plasma temperatures indicating progress towards commercial viability. 5. Focused energy. Technology, laser-driven fusion. Timeline, plans to build a demonstration facility in Germany by 2030.
Funding, supported by various grants including from the U.S. Department of Energy. Status, in early stages but optimistic about achieving operational status.
Future outlook. Despite these advancements,
many experts remain cautious about the timeline for commercial fusion energy. While significant breakthroughs have occurred, challenges remain in scaling up the technologies for practical electricity generation. Many startups claim ambitious timelines, but the historical context suggests that achieving operational fusion reactors may take longer than anticipated.
Conclusion.
The pursuit of nuclear fusion energy represents a promising avenue for addressing global energy demands sustainably. With a rich history, recent technological breakthroughs, and the emergence of innovative startups, the potential for fusion energy has never seemed closer. However, the journey from experimental research to commercial viability is fraught with challenges, and while optimism abounds, many experts advocate for a balanced approach that includes immediate investments in renewable energy sources alongside fusion development.
The next decade will be critical in determining whether fusion can fulfill its promise as a cornerstone of clean, abundant energy for the future. Counterintuitive information in the content. 1. Delayed commercialization versus
recent breakthroughs. While significant breakthroughs in nuclear fusion have recently been achieved, such as the ignition event at Lawrence Livermore National Laboratory, experts still caution that practical commercialization of fusion energy remains a distant prospect. This contrasts with the optimism expressed by some entrepreneurs and scientists who believe that fusion energy could soon be a viable alternative to current power sources. 2. Funding surge, yet skepticism remains. The influx of over $4.7 billion into fusion startups suggests a surge of interest and investment in this technology. However, despite this financial backing, many experts remain skeptical about the timelines these companies propose, indicating a disconnect between funding enthusiasm and realistic expectations about technological readiness and challenges. 3. Long-standing jokes versus genuine progress. The often repeated quip that fusion is always 30 years away reflects a historical pessimism about the technology's feasibility. Yet recent advancements, particularly in laser fusion and magnetic confinement, suggest that this narrative may be undergoing a transformation, challenging the notion that fusion is perpetually out of reach. For smaller startups versus large projects, the competition between small fusion startups and large-scale projects like ITER reveals a counterintuitive dynamic. Smaller companies claim they can achieve fusion energy faster due to their agility and innovative approaches, whereas ITER, despite its massive scale and funding from multiple governments, is criticized for its bureaucratic delays and complexity, suggesting that bigger does not always equate to better in the race for fusion energy. 5. Energy input versus energy output. The recent achievements in fusion energy, where experiments produced more energy output than input for the first time, still require a disproportionate amount of energy to operate the experimental setups. This highlights a significant gap between experimental success and practical energy generation, where current energy needs exceed what is produced, indicating that scaling up to a commercially viable reactor is still a major hurdle. 6. Safety perceptions. While nuclear fusion is often portrayed as a safe alternative to fission, the reality includes concerns about managing tritium, a radioactive isotope that is part of the fusion process.
The potential environmental risks associated with tritium release contrast sharply with the perception that fusion is inherently safer than fission.
7. Environmental impact versus timeframe. There is a growing consensus that while fusion power could significantly reduce greenhouse gas emissions and environmental impact,
its commercialization is unlikely to be timely enough to address the immediate climate crisis.
This juxtaposition emphasizes the necessity of investing in current renewable energy solutions alongside fusion research. 8. Public versus private sector efficacy. The argument that private companies could potentially outpace government-funded projects like ITER due to their nimbleness and focus contradicts the historical reliance on state-sponsored science for significant technological advancements. This evolving perspective on the effectiveness of public versus private investment in fusion research suggests a potential paradigm shift in how energy solutions are approached. 9. Funding versus readiness. Despite the substantial funding flowing into fusion research, many scientists emphasize that the field may not be ready for commercial application in the near future. This highlights a counterintuitive reality where financial investment does not necessarily correlate with immediate technological readiness, suggesting that traditional timelines for development may still apply. 10. Perception of breakthroughs. The recent achievements in fusion, while celebrated, are often followed by cautious interpretations noting that these milestones do not equate to immediate practical applications. This underlines a subtle skepticism in the scientific community about the implications of these breakthroughs, contrasting with media portrayals that celebrate them as imminent advancements in energy technology. These counterintuitive insights reflect the complex landscape of nuclear fusion research, where optimism and skepticism coexist and where the path to practical fusion energy is fraught with both challenges and potential breakthroughs.
Important overlooked content in the Nuclear Fusion Report.
The report on the history and latest advances in nuclear fusion research encompasses a wide array of topics from foundational theories to current breakthroughs and future projections.
While much of the report delivers critical information, several points may be easily overlooked yet hold significant implications for the future of energy production and global energy policy.
1. Historical context of nuclear fusion research. One aspect that often gets glossed over is the historical context of nuclear fusion research, particularly its ties to nuclear weapons development during the Cold War. The report mentions that fusion research began alongside atomic weapon development, which has implications for how fusion technology is perceived today. This association can lead to skepticism about the peaceful applications of fusion energy, especially in regions sensitive to nuclear issues. Understanding this history can provide insight into public apprehension and regulatory challenges that fusion technologies may face moving forward. 2. Recent breakthroughs and their implications. The report highlighted the December 2022 achievement of fusion ignition at Lawrence Livermore National Laboratory (LLNL). While this is widely celebrated, the significance lies not just in the achievement itself, but in the potential shift in funding and focus it may inspire. The successful ignition indicates that we may be nearing a point where fusion could be developed into a viable energy source, which could catalyze further investment in fusion startups and research. This momentum is crucial as it could lead to accelerated timelines for fusion energy deployment, potentially reshaping the global energy landscape. 3. Emergence of private sector startups. A notable trend that deserves more attention is the surge in private sector involvement in nuclear fusion. The report cites over $4.7 billion invested in fusion startups, suggesting a shift from predominantly government-funded projects to a more diversified funding landscape. The significance of startups like Helion and General Fusion lies in their agile approach to technological development compared to the bureaucratic processes of large-scale projects like ITER. This could result in faster advancements and more innovative approaches to achieving practical fusion energy, which may ultimately lead to commercialization before traditional projects can deliver results. 4. Diversity of technological approaches. The report delineates various technological approaches to nuclear fusion, including magnetic confinement, inertial confinement, and magnetized target fusion. A critical point that may be overlooked is the diversity of these approaches and the implications for scalability and cost. Different technologies may have varying operational efficiencies, capital costs, and timelines for commercial viability. For instance, while tokamaks have historically been the focus, other methods such as magnetized target fusion may present lower costs and quicker paths to operational systems. This diversification could lead to a competitive landscape that fosters innovation and drives down costs for future fusion projects. 5. Environmental and safety considerations. Another important yet often understated aspect is the environmental and safety profile of nuclear fusion compared to other energy sources. While the report mentions the lack of long-lived radioactive waste, it does not delve into the potential environmental impacts of tritium handling and the activation of structural materials. Tritium is a radioactive isotope that poses unique challenges in terms of containment and environmental safety. Addressing these challenges proactively will be essential for gaining public trust and regulatory approval for fusion projects. 6. Global energy policy implications. The discussion of fusion energy's potential as a solution to climate change is crucial but often oversimplified. While fusion promises a low-carbon energy source, the timeline for achieving operational fusion reactors may not align with the urgent need for immediate climate action. The report suggests that experts remain cautious about the commercialization timeline, emphasizing the importance of investing in current renewable energy sources alongside fusion. This dual approach is critical. Relying solely on the promise of fusion energy could lead to delayed action in combating climate change. 7. Public perception and investment risks. The report touches on skepticism surrounding fusion's timeline but does not fully explore the implications of public perception on investment. The repeated assertion that fusion is always 30 years away has fostered cynicism about the technology, which may deter potential investors and policymakers from committing resources. Understanding the psychological factors at play in public and investor perceptions can inform strategies to communicate progress and build confidence in fusion as a future energy source. 8. Long-term vision and international collaboration. Finally, the report presents a fragmented view of the fusion landscape with significant emphasis on national projects and private startups. However, it overlooks the potential for international collaboration to accelerate progress. Given the global nature of energy challenges, a coordinated international effort could pool resources and expertise, reducing redundancies and enhancing innovation. This collaborative approach could also facilitate knowledge sharing and technology transfer, crucial for overcoming the complex challenges associated with developing fusion energy. Conclusion. In summary, while the report provides a comprehensive overview of nuclear fusion's history and current state, it is essential to recognize the broader implications of the trends and challenges outlined. The historical context, the emergence of private startups, the diversity of technological approaches, environmental considerations, and the importance of public perception and international collaboration all play critical roles in shaping the future of nuclear fusion. Addressing these factors will be vital in realizing the potential of fusion as a safe, sustainable, and economically viable energy source for the future. 1. Historical context and development of nuclear fusion. Understanding the historical trajectory of nuclear fusion research is crucial. Originating in the 1950s, fusion studies were initially tied to nuclear weapons development before transitioning to peaceful applications post-1958. The shift towards international collaboration in the 1970s marked the beginning of large-scale projects like ITER, representing a collective effort to harness fusion as a viable energy source. This historical lens highlights the scientific and political challenges faced, emphasizing the complexity of turning theoretical concepts into practical, sustainable energy solutions. 2. Recent technological breakthroughs. The recent achievements in nuclear fusion. particularly the 2022 ignition at the Lawrence Livermore National Laboratory and the significant power output record at the European Joint Torus jet signal a pivotal moment in fusion research. These advancements suggest that fusion energy is closer to reality than ever before, igniting optimism in the scientific community and among investors. However, the technical challenges remain formidable, including scaling up these processes to achieve continuous net positive energy output suitable for commercial power generation. 3. Comparative analysis of fusion startups. The emergence of private startups alongside traditional research institutions marks a significant shift in the nuclear fusion landscape. Companies like Helion General Fusion and Gauss Fusion are leveraging innovative technologies and agile methodologies to accelerate progress. This comparison highlights the differences in approach timelines and funding strategies between established projects like ITER and these newer entities. The varying claims regarding prototype delivery timelines, ranging from 2028 to the 2030s, underscore the uncertainty and competitive nature of this field. For future outlook and challenges, despite the promising advancements, experts caution against overestimating the timeline for commercial fusion power. The consensus suggests that while fusion represents a potentially limitless and clean energy source, it is unlikely to resolve current climate crises in the short term. The emphasis on integrating fusion with existing renewable energy solutions and improving energy efficiency remains paramount. As the global energy landscape evolves, the fusion community must navigate scientific engineering and regulatory hurdles to achieve its ambitious goals. 1. The Manhattan Project 1942 to 1946. This was a secret U.S. government project during World War II aimed at developing atomic weapons. It brought together some of the most brilliant minds in physics, leading to the creation of the first nuclear bombs. The project's success was marked by the Trinity test in July 1945, which demonstrated nuclear fission. While primarily focused on weaponry, the scientific advances during this era laid the groundwork for subsequent research in both nuclear fission and fusion. 2. Cold fusion controversy 1989. In March 1989, chemists Martin Fleischmann and Stanley Pons announced they had achieved nuclear fusion at room temperature in a laboratory setting. This claim sparked huge excitement and controversy as it suggested a potential cheap and abundant energy source. However, subsequent attempts to replicate their results failed, leading to widespread skepticism in the scientific community. The cold fusion debate highlighted the challenges and complexities of fusion research and the scientific validation process. 3. The ITER Project 1985-present. The International Thermonuclear Experimental Reactor ITER is a collaborative project involving 35 countries aimed at demonstrating the feasibility of nuclear fusion as a large-scale energy source. Initiated during the Cold War, ITER represents one of the largest scientific collaborations in history. It seeks to replicate the processes that power the sun, making it a pivotal effort in the quest for sustainable fusion energy. Despite significant delays and budget overruns, ITER continues to be a central player in fusion research, with first plasma operations anticipated in the mid-2030s. Future outlook on nuclear fusion. The future of nuclear fusion holds immense promise as a nearly inexhaustible source of clean energy. However, the path to practical fusion power generation is fraught with technical challenges and uncertainty about timelines. Here are some predictions and insights into the future of nuclear fusion, considering its historical context, recent advancements, and the competitive landscape of current fusion startups. Predictions for technological advancements. 1. Increased investment and innovation. The fusion sector has seen over $4.7 billion in investments poured into startups, indicating a strong belief in the potential of fusion energy. This influx of capital is likely to accelerate technological advancements and innovations, especially from private companies that can operate with more agility than large bureaucratic projects. 2. Short-term breakthroughs. Following the recent achievement of fusion ignition at the Lawrence Livermore National Laboratory, We can expect more breakthroughs in inertial confinement fusion (ICF) and magnetic confinement fusion (MCF) technologies. Companies like Helion and General Fusion are focusing on innovative methods that may lead to significant milestones in the next few years, potentially achieving net positive energy output before 2030.
3. Commercial demonstration plants.
Startups such as Focused Energy and Tokamak Energy are planning to develop commercial demonstration plants by the late 2030s. These facilities aim to showcase the viability of fusion energy on a grid scale, with some predictions suggesting that working fusion reactors could enter the market by 2040. 4. Enhanced operational efficiency.
As technology improves, we can expect fusion reactors to achieve higher operational efficiencies and lower costs.
The goal is to produce electricity at a competitive price point compared to renewables and fossil fuels. A 1,000 megawatt fusion plant might cost between $2.7 billion and $9.7 billion,
making it feasible for widespread deployment. Challenges ahead. 1. Engineering and material science. Despite recent successes, significant engineering challenges remain.
Developing materials that can withstand the extreme conditions within a fusion reactor, including high radiation levels and intense heat, is crucial.
This includes the need for effective tritium recycling and the management of neutron activation in reactor components. 2. Long lead times. The timeline for commercial fusion power remains uncertain.
While some startups promise rapid advancements, the reality of engineering and regulatory processes could delay these timelines. Many experts still caution that real-world deployment may not occur until the 2040s or later.
3. Public and political support.
The success of fusion energy initiatives will depend on sustained public and political support. As the urgency of climate change increases, fusion may gain more attention and funding. However, it must compete with established renewable technologies like solar and wind, which are seen as more immediate solutions.
Market dynamics and competition. 1. Emergence of diverse approaches. The fusion landscape is becoming increasingly diverse, with various startups exploring different approaches.
From magnetic confinement to inertial confinement and magnetized target fusion (MTF), each method has its unique merits and challenges. This diversity may foster innovation and lead to breakthroughs in unexpected areas.
2. Collaboration and partnerships. Collaborations between startups and established research institutions are likely to grow.
This synergy can lead to shared knowledge and resources, accelerating development timelines.
For example, startups like Gauss Fusion are leveraging expertise from top research institutions across Europe. 3. Global competition.
The race for fusion energy is not confined to a single region. Countries such as the USA, China, the UK,
and members of the EU are heavily investing in their fusion programs. The competition could spur quicker advancements in technology as nations strive to achieve energy independence and sustainability.
4. Public perception and acceptance.
The perception of fusion energy will be critical.
As successes are achieved and public awareness grows, fusion may gain traction as a viable solution to climate change.
Education and outreach will be essential in garnering public support for fusion initiatives. Conclusion.
The future of nuclear fusion is filled with potential but is also laden with challenges. While the dream of harnessing fusion as a primary energy source is becoming more tangible, it will require continued investment, innovation, and collaboration across disciplines and borders. Although fusion energy may not provide an immediate solution to current energy needs, its eventual success could play a pivotal role in achieving global energy security and combating climate change in the decades to come. As research progresses, it is crucial to balance optimism with realism, ensuring that efforts in fusion do not detract from the urgent need to expand existing renewable energy sources.